Hello YouTube! In this video we're going to look at an important idea raised by James Bogen and James Woodward in their article Saving the Phenomena. This is the distinction between data and phenomena. This distinction has been quite influential in recent philosophy of science, and it has transformed the way that some philosophers have thought about scientific theories. So to explain this, we first need to go over the view of science that Bogen and Woodward were reacting to. So on the traditional view in philosophy of science, scientific theories are designed to predict and explain facts about observables, where something is observable just in case it can be perceived through the senses, or perhaps detected with instruments that might be taken to be extensions of the senses. So maybe we can observe things through microscopes and telescopes, say. This idea that scientific theories predict and explain observables, this is shared among many different approaches in philosophy of science. For example, according to traditional empiricists, such as the logical positivists, the vocabulary of scientific theories is divided into two parts. There are observation sentences, which report facts about observables. So, the thermometer reads 32 degrees, or there is a white streak in the cloud chamber. These are observation reports. Then there is the theoretical vocabulary, which contains terms defined by the theory for things that are not directly observable. Protons have spin 1/2, or white dwarf stars are supported against collapse by electron degeneracy pressure, are examples of theoretical statements. Of course, in the hard sciences, most of the theory will be expressed in terms of mathematics. Anyway, the theoretical vocabulary is linked to the observational vocabulary by means of correspondence rules, which allow us to derive observation sentences from theoretical sentences. So, from a theoretical sentence about electrons or protons or whatever, you can derive an observation sentence about what you will see in the cloud chamber. Prediction and explanation involve the deduction of observation sentences from the theory. Or consider, for a different kind of approach in philosophy of science, consider how contemporary scientific realists have argued that the observable extends beyond those things that are detectable with the unaided senses to anything that can be detected by means of reliable instruments. Realists may argue that we literally observe through microscopes and telescopes. Maybe we literally observe the interior of the sun by using neutrino detection methods. The assumption here is that the observable, the range of what we observe, is important in our understanding of science. Check out my video on observation in my scientific realism series for more on this debate. Or consider those philosophers who have challenged claims about scientific objectivity by arguing that observation is theory-laden. So we standardly think of observation as being a neutral arbiter between different theories. Theory T1 predicts observation X, theory T2 predicts observation Y, and then we run the experiment, see whether we observe X or Y. According to the theory-ladenness of observation, our observations are influenced by the theories we seek to test. Observations are not neutral arbiters. Check out my video on incommensurability in the Philosophy of Science series for more detail on this. Anyway, what's shared between all of these different views is a conception of science according to which scientific theories predict and explain facts about what is observed. Bogen and Woodward reject this picture. They hold that scientific theories don't do this. They don't typically predict and explain facts about what's observed. Indeed, they think that the notion of observation and questions about what counts as observable and whether observation is theory-laden and so on are really of very little importance to understanding science. They replace observation with a distinction between data and phenomena. Scientific theories are typically designed to predict and explain facts about phenomena, where phenomena are mind-independent, stable regularities in the world, which are often not observable. Examples of phenomena would be weak neutral currents, proton decay, chunking and recency effects in human memory, the melting point of lead, convection currents in the Earth's mantle, and so on. Phenomena such as these are detected through data. Data are often straightforwardly observed, but data are not predicted or explained by theory. Examples of data are bubble chamber photographs, patterns of discharge in electronic particle detectors, records of reaction times and error rates in psychological experiments, thermometer readings, records of magnetic anomalies on the sea floor, and so on. Data are particular measurements and observations, and data serve as evidence for phenomena. And it's the phenomena that are predicted and explained by theories. Of course, the term data isn't, although data are observable, there are many observable things that don't count as scientific data. So, like, I'm observing my cup on the table at the moment, but that's not a piece of scientific data. That's not like a datum that will support the existence of some phenomena. You get data after setting up particular experiments or special systems for measurement, let's say. So anyway, that's the distinction between data and phenomena. Now let's see how this plays out in a specific example. Let's consider the melting point of lead. The melting point of lead is a phenomenon in the world. It's a regular, stable property. It's a property of lead. Now, how do we come to know about this phenomenon? Well, we have to take a series of thermometer readings. What we actually observe, the data that we gather, will be a scatter of results around a mean of about 327.5 degrees C. But most of the measurements that we actually have will not be exactly 327.5 degrees. And this is because no matter how carefully we prepare our samples and no matter how well calibrated our thermometers are, our measurements will reflect not only the true melting point of lead, but a host of other sources of variation or error, many of them unknown and uncontrollable. These measurements are the data. And on the basis of this data, we then make inferences about the phenomena. We have to make certain assumptions. We assume that the sources of error operate independently, that they're just as likely to push the result in a positive as a negative direction, and so on. In that case, the data will have a normal distribution, and we take the mean as an estimate of the phenomenon, the melting point. So, key point here is that the outcome of these experiments will be a report of a phenomenon. We will say lead melts at 327.5 plus or minus 0.1 degrees C. We give the estimate and the standard error. This is not an observation report. It's not a report of what is actually seen. It's not a report of any particular data point. This statement doesn't represent any given data point. It's a result of drawing inferences from the data using some theory of statistical inference plus a bunch of other assumptions. Now, the melting point of lead is the explanandum of our theories. So it's the thing that our scientific theories will attempt to explain. The data from which we drew this conclusion are not potential objects of explanation by theories. So we can explain the melting point of lead by using a theory of molecular structure. But this theory could not explain the data gathered from the thermometer readings because the outcome of a particular thermometer measurement is dependent on a host of factors outside the domain of theories of molecular structure. The thermometer reading will be influenced by the purity of the sample, by interactions between the sample and the container, by the internal operation of the thermometer, by the way the thermometer is used and read by the experimenter, by the interaction between the thermometer itself and the sample, by various outside factors like magnetic field and electric charge and whatever. Our theories of molecular structure simply do not cover, they don't predict and explain all of these processes. So you're not going to predict and explain all of the data points or even some of the data points by applying the theory of molecular structure. Similarly, consider general relativity. General relativity predicts a particular value for light bending around the sun. The effect of a mass on the path of light is a phenomenon. There are various ways of detecting this phenomenon. Famously, Arthur Eddington took some photographs during the 1919 total eclipse. The data collected on these photographs was affected by various factors. So the influence of the Earth's atmosphere on light from the stars, the temperature of the air affecting the photographic plates, Eddington's decisions about where to position his camera, and so on. Now, general relativity is a theory of gravitation. It explains gravitation and related phenomena. It doesn't explain the operation of cameras, telescopes, the optical properties of Earth's atmosphere, or the psychological factors influencing Eddington's decisions concerning how to design his experiment. So again, the data is not explained by the theory being tested. Indeed, the data isn't explained by any theory. While we have theories that cover some of these factors, so like we have theories concerning the optical effects of the atmosphere, some are not covered by any theory whatsoever. Some factors are just unknown and uncontrollable. So phenomena can occur in a wide variety of different contexts. They are the result of a small number of causal factors they occur in different contexts and they can be isolated for study. The melting point of lead, that's a result of the structure of lead atoms. Data are idiosyncratic to particular experimental contexts. They are dependent on specific data gathering procedures, and there are many causal factors involved in their production. These factors are numerous, uncontrollable. Theory cannot trace them in detail. Phenomena are stable regularities, which can be detected with a wide variety of different procedures, producing very different kinds of data. So take the detection of weak neutral currents. These were detected in 1973 independently at CERN and NAL. The CERN data consisted of about 290,000 bubble chamber photographs. 100 of those contained evidence of weak neutral currents. The NAL data was 330 records of patterns of discharge in electronic particle detectors, and 8 of those provided evidence of weak neutral currents. So, same phenomenon, very different data, very different types of data there. The phenomenon of weak neutral currents occurs in all kinds of circumstances, such as, whenever a neutrino strikes a nucleon. On the other hand, the data from bubble chamber photographs, that occurs only in a few laboratories. Indeed, the specific data that was gathered at CERN, well, that occurs only at CERN and nowhere else. Even if we tried to repeat the experiments exactly as they were performed at CERN, we would obtain different data due to uncontrollable sources of error. So, the picture favoured by Bogen and Woodward looks something like this. This diagram is taken from Samuel Schindler's article, How to Discern a Physical Effect from Background Noise. Theories explain phenomena. Phenomena are regularities in the world, often unobservable. Not necessarily unobservable, actually. There may be some observable phenomena, but they're often unobservable. Data serve as evidence for phenomena, and the up arrows from the data, those show the bottom-up inference that we make from data to phenomena. The down arrow that you can see from phenomena to data, where it says phenomena produce data, that is because that's representing a causal relation, right? Phenomena play a causal role in the production of data. So the melting point of lead plays a role in the thermometer readings. The chunking effects in human memory play a role in the reaction times recorded in psychological experiments. We can see how this challenges the traditional view of the structure of scientific theories. To say that scientific theories predict and explain facts about what we observe would be to make the mistaken assumption that theories predict and explain facts about data. But theories don't really have any relation to data, right? We establish the reliability of data and the existence of phenomena independently of the theory. Now, this diagram is a simplification, I should say. Bogen and Woodward do not claim that scientific theorizing always works like this. Some scientific theories may well predict and explain observations or data. Bogen and Woodward suggest that early astronomy was like this. The early astronomy was literally just concerned with capturing data in the theory. But in more mature sciences, the data phenomena distinction becomes significant. Procedures for data analysis are developed which allow scientists to uncover stable phenomena in the world, and so theories no longer have to account for what is directly perceived. So, as I've said, a key part of this account is that we establish the reliability of data and the existence of phenomena largely independently of the theories designed to account for those phenomena. Now, this is not to say that inferring from data to phenomena is easy. Indeed, the inference from data to phenomena may involve actually quite sophisticated theoretical ideas, so procedures for data reduction and statistical analysis. It's just that these ideas will be shared by the theories that are actually being tested against the phenomena. We must also ensure that the instruments we have used are properly functioning. This requires methods for controlling confounding factors. If we're running an experiment using a particle detector, then there will be many other particles that would produce the same effect as the particles we're trying to detect. So instruments for detecting neutrinos will respond to many other particles as well. There's no point trying to develop a detailed causal theory of all these influences so that we can rule them out from our data. Instead, we simply shield the instruments, say by placing them underground. Or consider again Eddington. Eddington found that the high ambient air temperature was distorting his photographic plates. He was able to correct for this distortion through an empirical investigation of his instrument. The theory he was testing was general relativity, and he didn't need to apply that theory in order to ensure that his instrument was reliable. So in the inference from data to phenomena, we may apply statistical theories, methods for calibrating instruments and so on that are independent of the theory under test. A good indication of the independence of phenomena from sophisticated theory, it can be found when we examine the history of science. Theories that specify fundamental systematic explanations, theories that tell us the basic causal mechanisms, these often change over time, while the phenomena tend to remain stable. Take, for instance, our theories of light. There was the corpuscular theory, according to which light consisted of discrete particles. Then there was the early wave theory, which developed into the more sophisticated electromagnetic theory. And then finally there was quantum theory, which treats light as having wave-particle duality. These are fairly radical theoretical changes, and yet the various phenomena that prompted the development of these different theories have been retained in our science. So Newton's corpuscular theory could easily explain why, when light reflects from a surface, the angle of incidence is equal to the angle of reflection. Or take one of the crucial experiments in establishing the original wave theory of light, the demonstration of the Arago spot, which is a small bright spot at the centre of a shadow of a circular object. The corpuscular theory couldn't account for that, but if light consists of waves, we can easily explain it as arising from diffraction. Now, these phenomena, and many other phenomena associated with reflection, refraction, interference, diffraction, and so on, have endured through changes in explanatory theory. Our understanding of these phenomena and our mathematical treatments of them remain pretty much the same as when they were first discovered. And this is not unique to theories of light. You find the same retention of claims about phenomena across all disciplines. But obviously, if judgments about the reliability of data and the inference of phenomena from data, if that was dependent on these high-level theories, then our claims about phenomena should be on far shakier ground than they in fact are. But they're not. Phenomena tend to be independent of theory and are established independently of theory. There is an obvious objection at this point. You might say, okay, sure, thermometer readings will be influenced by many factors outside the domain of theories of molecular structure. Eddington's eclipse photographs influenced by factors outside the domain of general relativity, so it is for all data. Nevertheless, it must be possible in principle to derive claims about data from scientific theories when those theories are conjoined with suitable auxiliary hypotheses. So general relativity alone does not predict or explain Eddington's data, but we take general relativity and add models describing the camera equipment, the telescope, the conditions in the Earth's atmosphere, and so on. In principle, you could have models for all of what we might see as sources of error. So in principle, there is a complete theory that captures all the causal influences on Eddington's data. Furthermore, this kind of thing is what science ideally aims at. Scientists do, in fact, attempt to account for the patterns that they observe in data sets in greater and greater levels of detail. And when they make predictions or give explanations, they do in fact try to draw on a variety of relevant models and theories. So, Bogen and Woodward's response to this point is, well, it's simply trivial. Like, as long as we're assuming a broadly physicalist metaphysics, then obviously it's possible in principle to predict and explain data. That would just be a matter of describing all the causes of the data. Well, actually, I guess you'd have to assume the world is deterministic, because if it's indeterministic, then it might not be possible, even in principle, to predict it. But certainly it's possible in principle to explain it. But anyway, this tells us nothing about how scientific reasoning actually works, right? Like, this is the problem. This just doesn't tell us what's actually going on when scientists construct their theories. So not only does it not tell us anything about how scientific reasoning works, but it wouldn't actually be particularly useful to have this kind of thing. So, we can imagine the complete theory as being a kind of ideal to which science aims, but, obviously we're not there yet, and actually that's not something that we would really want. It would be useless. So, there's that famous story by Jorge Luis Borges, or however his name is pronounced, of the cartographers who, in their attempts to create an ever better map of an area, they end up just building an exact replica of the area, right? Which is kind of useless as a map. And the same would be the case for a complete theory. That, like, the complete description of everything in the world, or everything in some particular system in the world, wouldn't provide us with the kind of knowledge that we're looking for, that we need. We need to be a bit more selective. So while we can, in principle, derive claims about data from the general theory plus suitable auxiliaries, in practice scientists don't use such derivations. Eddington does not infer downwards. He doesn't infer from facts about worldly systems to his data. Instead, he infers upward from the data to the phenomena. He infers from the features of his photographs, plus certain background assumptions, such as aspects of statistical analysis, to a value for the deflection of starlight by the sun. And what would be the point in doing otherwise? There was never any need to provide an explanation of the data. What made the data important was that they served as evidence for the phenomenon. Still, I mean, why is this, right? Like, we might accept that Bogen and Woodward's account is descriptively adequate of how scientific reasoning works, but still wonder whether this is an appropriate way to proceed. Now, in fact, Bogen and Woodward argue that scientists are indeed justified in foregoing explanations of data, and this is because we require scientific theories to provide what they call systematic explanations. Systematic explanations possess two important features. First, a systematic explanation must reveal, in detail, the patterns of dependencies between things. When we explain some event X by appealing to some other factors Y, we must show how the features of X depend on the features of Y. So suppose we wish to explain the operation of the optical microscope. Well, it would be useless to say something like this. Okay, the image is produced by the way light interacts with the specimen and then enters the microscope, and the microscope magnifies the image. Right? I mean, that's true. That's actually a true explanation, but it doesn't provide any details about the actual mechanisms involved. We need to know the optical laws. We need to know the behavior of light and its interaction with the specimen. We need to know how the image is produced by the interference of transmitted and diffracted rays, and so on. We require some sort of model of the internal operation of the microscope and how light interacts with it. So basically, in a systematic explanation, we learn in detail how altering the factors cited in the explanans would alter the factors cited in the explanandum. So we know when we explain some event X by appealing to other factors Y, we know how altering the Y factors would alter the X factors. With a proper explanation of the microscope, we will learn how changing certain bits around would increase or reduce chromatic aberration, for example. A second feature of systematic explanation is that it unifies a range of different kinds of things. It shows the connections between a range of seemingly independent things. So seemingly independent facts are accounted for in terms of a small set of mechanisms or laws. Newtonian mechanics unifies the swing of a pendulum in the orbits of the planets, insofar as these are both captured in the Newtonian models. Maxwell unified electricity and magnetism. The wave theory of light permits the explanation of various optical phenomena associated with reflection, refraction, diffraction, stellar aberration, and so on. Darwinian natural selection explains adaptation, the geographical distribution of species, vestigial traits, homologous traits identified in comparative anatomy, the rise of antimicrobial resistance. All of these seemingly different things captured under the auspices of a single theory. So systematic explanations have this unifying power. Now, with all of this said then, let's consider potential explanations of the data. In the case of data, well, since there are so many idiosyncratic causal factors involved in the production of data, the patterns of dependence are often just inaccessible. Like, we just can't know all of these causal factors, and it would generally be kind of pointless to uncover them. An explanation of even a few data measurements would be extremely complex, and it would be tied to the details of some particular experimental arrangement. Like, if you change the detection method, then the explanation of the data would have to change very significantly. A scientist attempting to explain just a few data points would have to give numerous, highly local, independent explanations, even if those data are measuring the same phenomenon, right? Like, consider the different data of melting points that you'd get by using a mercury thermometer versus a gas thermometer. Like, just think about how different the explanations would be if you were trying to trace all of the causal influences there. So explanations of data will fail to have the features that we expect of good explanations. First, because we're often simply unable to cite all or even most of the relevant causal factors, or even if we can cite all of the relevant causal factors, the interactions between them will be so complex as to be computationally intractable. And second, because even if we could give the complete causal story, it would lack generality. It would fail to provide any significant theoretical unification. By contrast, the kinds of dependencies uncovered in explanations of phenomena are accessible and important because phenomena involve relatively few causal factors and occur in a wide variety of circumstances. Once we know the conditions under which weak neutral currents occur, or once we know the way in which mass affects the path of light and the reasons why this happens, we can apply these explanations to a variety of systems in nature. And we can also use this knowledge practically to help us manipulate and investigate nature. We can build instruments that exploit these regularities. So scientists focus on explaining phenomena because they want to focus on what is stable across different contexts. They want to show how a few causal factors or a few general principles apply to a wide range of cases. Now, one of the most influential objections to Bogen and Woodward has been proposed by James McAllister in his article Phenomena and Patterns in Datasets, who argues that Bogen and Woodward's conception of phenomena is incoherent. So we have seen that for Bogen and Woodward, phenomena are part of the world. They are objective features of reality. We might even say they are natural kinds. Importantly, they would say that what phenomena exist in the world is not dependent on the interests or goals of investigators. It's not dependent on how we think about or conceptualize the world. Basically, phenomena are discovered, not constructed. Now, as we've seen, phenomena manifest themselves as patterns in datasets. So we detect a phenomenon by identifying a particular pattern in a dataset. Now, particular types of patterns in datasets then correspond to the phenomena. And McAllister suggests there are two basic claims here which are incompatible. So first, there's the claim that phenomena are objective, they're not a matter of stipulation. And second, there's the claim that phenomena correspond to patterns in datasets. These two claims are incompatible. And the reason for this incompatibility is that a dataset, no matter what type of data it is, consists of two components. First, there'll be some sort of pattern. This is something fairly simple, fairly regular, or at least usually. And then second, there will be a certain level of noise. So there's signal and noise, right? The signal corresponds to the phenomenon. The noise consists of the various extraneous background influences and is responsible for the scatter of the data. This is all perfectly familiar. The problem here is that any data set can be described in terms of infinitely many patterns with different levels of noise. So you can have pattern A plus noise at X%, pattern B plus noise at Y%, and so on. We could also just set the noise at 0%, and then the pattern of the data will be the extremely complex pattern that exactly matches the data constituting the data set. So, let's say that you have a data set of measurements of the orbit of Mercury. Well, if you take this with 0 noise, you have a pattern that exactly reproduces the data. With different non-zero noise levels, you can get infinitely many other patterns out of this data. You can get particular circles, ellipses, more complex curves. For Kepler, taking the data with a relatively high noise level, the planetary orbit of Mercury is an ellipse. For Newton, assuming a lower noise level, it's a curve that approximates an ellipse but differs due to the gravitational interaction with other bodies. For Einstein, with an even lower noise level, again, we have a similar curve, but there are slight differences due to the relativistic effects because Mercury is so close to the Sun. Now, Bogen and Woodward will claim that only some of the infinitely many patterns in a dataset correspond to a phenomenon. And this, of course, raises the question of how exactly we distinguish the patterns that correspond to phenomena from the other patterns. Where do we fix the noise level, and what reason justifies fixing the noise level at this point? Well, clearly we can't suppose that phenomena correspond to patterns in datasets with 0 noise. This pattern is just equivalent to the dataset itself, so this would obviously undermine Bogen and Woodward's reasons for introducing the data phenomena distinction in the first place. But it's also clear that if we fix the noise the noise level at some non-zero level, this will simply be a matter of stipulation by the investigators, because there's nothing in the dataset itself that tells us what the appropriate noise level is, right? Like it's not as though particular patterns come labelled as being patterns that correspond to the phenomena. No, the dataset itself doesn't tell us what the appropriate noise level is. So the phenomena then, the pattern that corresponds to the phenomena will become partly a matter of stipulation. What phenomena the world contains will depend on decisions made by the investigators, which of course contradicts Bogen and Woodward's assumption that phenomena are objective features of the world. Now, McAllister accepts the data phenomena distinction, so he's with Bogen and Woodward on their view of the way that scientific theories are structured, but he thinks that phenomena are investigator relative, so he rejects that claim 1, the claim that phenomena are objective. Investigators must stipulate exactly which patterns correspond to phenomena. One way to do this is by fixing a particular level of noise in a data set, and typically those patterns that we designate as phenomena will simply be those patterns that we're interested in studying or explaining. So the way McAllister explains this difference is that for Bogen and Woodward, we can think of the world as being composed out of a relatively small number of stable regularities which occur in a wide variety of contexts and which cause patterns in data sets. And these stable regularities are phenomena. On McAllister's account, by contrast, the world is, as he puts it, simply a complex causal mechanism. There's just like loads of stuff going on. It's just messy and complex, and there's all sorts of different things happening, and any given system will produce data in which there are infinitely many patterns. We then designate some of these patterns as being interesting objects of study for one reason or another, right? So we have these data sets, and we just find some of the patterns that we find in these data sets interest us, and those are the ones we designate as phenomena. Take the example of the melting point of lead. As we've seen, when we measure this melting point, we get a scatter of readings. On Bogen and Woodward's account, we apply various techniques to draw out of these readings a horizontal line, which corresponds to the, because you can imagine plotting all of the data set on a graph or something. So you plot the data set and you find this kind of scatter, and applying the statistical techniques, we draw a horizontal line which corresponds to the phenomenon, the invariant melting point of lead. This melting point is the explanandum of theories of molecular structure. But of course, there are all kinds of patterns we might discern in our data sets. These patterns may show the melting point varying. They may reveal its dependence on air pressure, on electrostatic charge, on magnetic field, on the structure of the container, on the materials of the container, or some unknown physical parameter. On Bogen and Woodward's view, these factors are sources of error. But of course, scientists can and do take any of these things as their explanandum, as the thing they want to explain. One scientist may take the invariant melting point as the explanandum. They may try to explain, say, why the melting point of lead differs from the melting point of mercury, right? Like if that's your question, if you're asking about the difference between the melting point of lead and the melting point of mercury, then of course you're just going to focus on like the invariant melting point. You're just going to, as it were, draw a horizontal line through the data. But another scientist might try to explain how the melting point of lead is dependent on magnetic field or on the structure of the container or whatever. She will take other patterns as her explanandum. And if we look at the history of science, we do in fact find that scientists will try to account for patterns with lower and lower noise levels. So that is, they try to give increasingly precise accounts of the data. Indeed, notice that the melting point of lead is in a sense an idealization. In order to have a fixed melting point, you would need a perfectly pure sample of lead, and you would need to precisely fix the features of the environment and the measuring equipment. But of course, we never do this. We can never do this. We can never remove all sources of variation. And even if we could construct like this pure sample in a precisely fixed environment, the world itself, the rest of the world is far more messy. So the phenomenon of the melting point of lead, the invariant melting point of lead, that's not something that ever actually exists in the world. It's to some extent an abstraction. So on this point, it's worth checking out Hasok Chang's work on temperature. We had to set up experimental situations very carefully in order to create relatively invariant melting points and boiling points. Hasok Chang has a great book called Inventing Temperature, but I'll put up a link to some of his other work that's freely available. Anyway, so these are not phenomena that occur in the world with like stable regularity. They're not phenomena that can be found in a wide variety of different contexts. You only find the melting point of lead in a wide variety of different contexts if you are choosing a particular pattern to draw from your data sets. Now, it's important to note that McAllister is not a social constructionist. He's not claiming that scientists literally construct the world or anything like that. The physical events that are investigated by scientists, say the motion of a planet or the melting of a particular sample of lead, these are exactly the same for all the scientists examining that system. But, as Bogen and Woodward themselves have argued, our theories do not attempt to explain all the aspects of a particular system. That would amount to explaining every single data point. Instead, we focus on particular patterns, say the planet's orbits being ellipses, given a certain noise level. The noise level here just designates the many physical interactions outside the domain of the given theory. But we can always set the noise level lower. We can always try to capture more within our theories. The key point is that the patterns we try to explain, and so the patterns we designate as corresponding to phenomena, is fixed by investigators, not by the world. So what counts as phenomena is partly up to us. It's partly a matter of what we decide to investigate. And so this challenges Bogen and Woodward's account of phenomena as being objective features, while still retaining their overall view of the structure of scientific theories as explaining phenomena and phenomena being inferred from data. Anyway, as I say, this is an idea that has been quite influential in contemporary philosophy of science. I hope you found that interesting. That's all for today. Goodbye.